Okay, well, good afternoon, everybody. Welcome to this month's IRIS US Array webinar. This is a webinar that's organized by the Transportable Array Working Group to highlight some of the EarthScope-related research that IRIS enables. If you don't, this is your first webinar or you don't recognize this voice, this is Andy Frassetto. I'm broadcasting live from the Incorporated Research Institutions for Seismology headquarters office in Washington, D.C. For those of you who aren't familiar, IRIS is a approximately 30-year-old nonprofit consortium of universities. It's also a science facility funded by NSF to operate programs that enable a broad spectrum of geophysical research. If you don't know me personally, I'm the IRIS Project Associate, aka Swiss Army Knife, that helps to manage the EarthScope US Array, as well as the Global Seismographic Network, and some of the other seismology research programs that are housed out of IRIS. The webinar series was initially developed to highlight some of the science done under these programs, so I'm excited to bring you today's webinar. Previously broadcast webinars are archived off of a specific webinar webpage. And so I have my screen shared with you guys. And so I just wanted to highlight that page in case you were curious in checking out some of the previous webinars. So the address is www.iris.edu/HQ/webinar. And if you go to that page, it has listed the webinars that are either, in this case, today's, and then also upcoming, as well as the previous ones, which if you click on a thumbnail, it will take you to the YouTube page. So you can go through that and access any of the topics that you might have missed in the past. Today's webinar is going to be recorded and posted on here within a couple of days. So if you see the webinar and think that a friend of yours is going to really like it, then feel free to pass that along to them. Just a few guidelines for how this works so that we're all on the same page. I'm going to unmute Fan Chi to give his presentation, and he and I will be the only two people who will be able to speak. If you have a question for Fan Chi or for myself as the webinar is unfolding, type it into the question box on your webinar control panel, and I will see that. It'll pop up on my screen, and I will be able to either respond to that if that's a technical question within the webinar, or if it's a question for Fan Chi, we will go through that afterwards in a Q&A session where I'll just sort of read him the questions that everybody has submitted. If the webinar has a little crash, this has only happened once, but just give it a moment and use the same link that you got in your registration email. And so I should be able to reboot it from my end, and you should be able to get back into it from your end. Also, this is just for my sort of personal curiosity. If you're part of a group that's watching this webinar, so it's more than just you in the room, just shoot me an email afterwards or send me that information in the question box. Just trying to keep a little survey of how many additional viewers we have for these things when we broadcast them. The other thing that I wanted to do for this webinar is I always like to try to tie in data products that IRIS is developing that are some way related to the webinar topic. And this is actually a good opportunity this week to share what we call the Earth Model Collaboration. So this is a data product that's been developed by the IRIS DMC. And so it's at www.iris.edu/DMS, stands for Data Management Systems, /products/EMC. And this is a way to do a standardized comparison of Earth models. And so if you have an Earth model that you'd like to add to this, if you can set it to them in a unified format, like it's a NetCDF is what they use, then they're able to load that in and have that directly comparable to other models that have already been provided. So I just wanted to show a quick example of what this is like. So if I'm going to go on this and I want to look at horizontal slices through the Earth, if I clicked on that under Visualization Tools, it goes to a page where you can then specify what model you want to use, and also some of your plotting parameters in terms of depth of the slice, bounds for the map view box, as well as you can even specify your color palette and how much you want to adjust that based on what you're looking at. And so a lot of scientists often will do stare and compare. Well, they'll take two figures plotted in different ways with different color palettes from different papers and try to get those as close as possible in Illustrator. This is an opportunity to more directly qualitatively as well as quantitatively compare Earth models, since they're also available in their original NetCDF format. So I would encourage everybody to take a look at this. If you have any questions, you can of course ask me, but also Manoush Bahavar and Chad Trabant and Alex Hutko are some of the data products people at the DMC who are actively developing these products. And so if this is something that you're interested in or want to participate in, they're the people to speak with directly. And I think they're working on a lot of really cool stuff. So I just wanted to highlight that, since a lot of Fanchi's talk will be dealing with both seismic tomography and deep Earth imaging. So I think without further ado, I will switch back over into webinar mode and pass control over to Fanchi in just a second. I just want to introduce our speaker today. So our speaker is Dr. Fanchi Lin. Fanchi is a postdoc at the California Institute of Technology, Caltech. He's originally from Taiwan. He received his master's from Drexel University, and his PhD was working with Michael Ritzwaller at the University of Colorado. So I think without further ado, I will pass it over to Fanchi, and his talk will be titled Seismic Interferometry and Tomography from Shallow to Deep. And so Fanchi, there's going to be a brief hiccup in the audio when I send it over to you. So just be aware of that. You should see this come up on your window, and I'll make sure that you're unmuted. Okay, I think I can hear you.
Okay, let me turn. Can you see my presentation?
And it looks like it's loading. Yes, there's your title slide.
Okay. All right, great. All right, so thanks for the introduction. So I'm Fanchi Lin. I'm at Caltech right now. I'm a postdoc here. And it's my pleasure to present some of our recent research on using seismic tomography and interferometry to study Earth structure from shallow to deep. So mostly I'm going to show the research I've done using the US array, but in the later of the talk, I will also discuss some of the very localized dense array application. So let's see. Before I jump into the science, I just want to acknowledge some of the people that kind of contribute to the research I done. And so the first one is Mike Ritzwaller, who is my PhD advisor at the University of Colorado at Boulder. And Victor Tsai and Rob Clayton are both faculty at Caltech. Don Julie is a grad student at Caltech, and Brendan Schmidt was previous postdoc at Caltech, but now he's at University of New Mexico. So why we are interested to study Earth structure? If you look at the topography of the U.S., you can see that there's a lot of variation. For example, on the western side, you have this higher topography and rougher surface. But if you go to the eastern side, it's more flat, and there's almost not much going on there. So also on the western side, we have more tectonic activity, a lot of volcanism. For example, in the Washington, we have Mount St. Helens, and also in Wyoming, we have Yellowstone volcanism. So in general, on the western side, it's more active, tectonic active, and on the eastern side is tectonic more stable. So we would like to understand what's the crust and upper mantle structure, and like how that kind of relate to the surface feature we can observe. And more than that, if we understand the 3D Earth structure better, we can also explore the nature resource such as the oil in the shallow crust, or we can also understand the high seismic hazard. For example, the San Andreas fault shown here, or this is the image after a big earthquake in Christchurch, New Zealand. So if we understand the 3D structure, we can understand both nature resource as well as seismic hazard a little bit better. So the tool we are going to use is seismic waves. And here I'm just going to show animation, just get a big picture on how those waves propagate. So after an earthquake, for example, happened near the surface, then you have P wave going down, S wave going down. P wave is red, S wave is green color, and then you also have this surface wave propagating near the surface, which is much slower than the P wave and S waves. And so this surface wave, because it's very sensitive to shallow structure, it's particularly nice to use this surface wave to study near surface features. And in general, there's two types of surface wave, one called love wave, one called Rayleigh wave. For love wave, if the wave is propagating to the right side, the particle motion is always perpendicular to the direction of propagation. So it's in the horizontal direction, but it's perpendicular to the direction of wave propagation. For Rayleigh wave, on the other hand, the particle motion is on both the direction of wave propagation as well as in the vertical component. So actually, here is a very nice animation showing the particle motion of Rayleigh wave, where you can see that it have movement in both radial direction as well in the vertical direction. So in the later of the talk, mostly I'm going to discuss how we can use this Rayleigh wave to study shallow Earth structure. So here shows an example of what we can do with a seismic array. So if you have an earthquake, for example, for the Tohoku earthquake in 2011, after the earthquake, the wave will propagating both within the Earth as body wave as well as near the surface as surface wave. And if you have an array such as US array over here, then you should be able to see both body wave and surface wave propagate across the array. So if I let this animation run, so for each station, the color will describe up or down motion, and you will also see a little bar describe the horizontal motion. So let me just play this. So after the earthquake, the first thing arrive is P wave, which is mostly up and down. So you will see blue and red go across it. Then you start to see a lot of S-related body waves. So you can see there's a lot of motion over there. Then you got love wave, which is always perpendicular to the direction of wave propagation. And then you got Rayleigh wave, which is this kind of rolling motion. So by studying surface wave in particular, it will allow us to study structure right beneath this array. And after the surface wave, you still have a lot of signal, but it's usually referred as coda. And this coda potentially can also be used to study Earth structure. So in principle, if you have one earthquake, you have one station, then you can make seismic measurements. So here shows a global seismicity map. So basically, you can see that the earthquake is not very, it's distributed somehow unevenly. It's mostly happen near the plate boundaries. For example, near the Pacific plate, you have a lot of earthquakes, but within the Pacific plate, you have very almost no earthquake at all. This is it's true for continents. For example, on the western side of the U.S., you have a lot of earthquake, and on the interior side, you have almost no earthquake at all. So in a way, this type of uneven distribution actually limits some of the seismic image application. But on the other hand, for a seismic station, you can see they have very different distribution from global seismicity. Mostly, all the station is distributed on the continent. And in general, we have better control on where we want to put the stations. So in a way, it would be much nicer if we can extract wave propagating between two stations, not just only between an earthquake and a station, but if we can kind of extract information for wave propagating between two stations, then that will give us a better tool to study some of the very shallow structures. So that comes to lead to seismic interferometry. So what seismic interferometry does is that if you have an area and you have a lot of noise source, so all the red dots are imaginary like noise sources, and if you put two stations in this area, and you observe this kind of noisy waveform, and it's very hard to extract useful information directly from looking at this type of noise wave field. However, if you do cross correlation between the noise wave field observed at these two stations, so we calculate the cross correlation function, and if actually the cross correlation function will show a very clear signal For example, on the negative side, you have this signal. On the positive side, you have this signal. And they are actually corresponding to wave propagating between those two stations. For example, on the right-hand side, it's equivalent to if you have a point source on the first station and what you will observe on the second station. On the other hand, for the negative side, this signal is corresponding to if you have a point source on the second station and what you will observe at the first station. So if this works, that means we can put station anywhere on the globe, and we should be able to extract wave propagating between those two stations. And we think it will work for the Earth because we know that there's a lot of noise source on the Earth. You have oceanic perturbation, you have automatic perturbation. There's all kind of noise source we can imagine. And so it's likely this method will work on the Earth. And it definitely works. Otherwise, I'm probably not going to give this talk here. So if you take two US array stations as an example, take station 1, station 2, which are 116A and RO6C. And we have 3 component seismogram, vertical, radial, and transverse for both two stations. And we can do cross-correlation between different components. And the result for 1 year cross-correlation is shown on the right over here. So for vertical cross-correlation, so in this case, it's equivalent to if you put a point source at a station 1, put a vertical point source at station 1, and what you will observe in the vertical component in the second station, which actually is the Rayleigh wave, because vertical force will excite Rayleigh wave propagating, arrive in vertical component. So you can see the Rayleigh wave in both positive side as well as negative side. And you can also do this for radial cross-correlation. In this case, it's equivalent to if you have a point source in radial component. And of course, this will also excite Rayleigh wave, and it will also show up in the radial component. So you can actually see this Rayleigh waves for both vertical and radial cross-correlation, and they arrive at the same time. On the other hand, if you want to get love wave, what you do is you excite, you need a transverse direction force. So you do transverse cross-correlation, and the love wave will propagating in this direction and arrive in the transverse direction component as well. So you can see that this is the love wave, and usually love wave propagates slightly faster than Rayleigh wave, so it's arrived a little bit earlier compared to Rayleigh wave shown here. So to see what happens if you have an array and how we can use this to this technique basically to produce a virtual source. For all these stations here, if you do cross-correlation between this center station, which is R06C, you can do cross-correlation between this station to all other stations. And so in here, I show the vertical component cross-correlation. And you can see that for different distance, different station pair distance, you can see that for the signal actually arrive in different time. Actually, you can see that the farther the distance is, the later it arrives. And this is actually the move out of Rayleigh wave. And we can also see the energy distribution for each snapshot in time. For example, at 100 seconds, if we cut a line over here and plot where the each cross-correlation, what the amplitude is on the map here, you can see that at 100 seconds, mostly the energy arrive at those stations. And then if we go to 200 seconds, draw another line here, and you can see the energy actually arrive later, farther away. So you can see actually how the by cross-correlation between one station to other station, you can equivalent to produce a virtual source here, and the energy kind of radiate out. And actually, we can produce an animation here. On the left-hand side, I'm going to show the cross-correlation between this station to other station, but it's vertical cross-correlation, which will give us Rayleigh wave. On the right-hand side, I'm going to show the result for transverse cross-correlation, which will give us love wave. And you can see that when I start the animation, you can see the energy move out in all directions. And if I stop here, you can see that in general, on the right-hand side, the love wave, the circle is a little bit larger than on the left-hand side because love wave propagates slightly faster. And here, I just want to emphasize again, there's no earthquake happen at this location. So there's no earthquake at all. This is all based on ambient noise cross-correlation. So effectively, this technique allows us to create a virtual source wherever we can put a station there. And the nice thing about this technique is that because right now we can basically use very close by station as a source, we can extract some of the very high frequency surface wave. So for different period of surface wave, actually the sensitivity to depth is a little bit different. For Rayleigh wave on the left-hand side, for example, if you measure this long period surface wave, then you are mostly sensitive to deeper structure. For example, 100 seconds, you are mostly sensitive to this very broad depth region, and it's mostly beneath 100 kilometers. And if you really want to study very shallow structure, then you need to go above 26 seconds. So this is the earthquake band, but if you can do ambient noise, you can go from 1 second all the way to 30 seconds. So it's provided a very unique tool to study crust and uppermost mantle structure. And it's the same for love wave, where the higher frequency, the signal is more sensitive to shallow structure. And longer the period, the deeper it's sensitive to. So before I jump into surface wave tomography, I just want to mention that recently we also start to extract body wave out of ambient noise cross correlations. So here shows an example that if we stack all the cross correlation within the US array and sort it based on different distance. So here from 0 to 2,000 kilometers, and the time is from 0 to 3,000 seconds. And beside the Rayleigh wave signal over here, we can actually also start to see a lot of other phases. For example, here is the SCS phase, here is the PKIKP phase, which are both body wave phase predicted by the 1D model. And what those phases are actually the reflection. For example, SCS is the reflection of S wave out of core middle boundary and arrive back at the same array. And PKIKP2 is the wave going down through mantle, outer core, inner core, arrive at the other side of surface and reflect back and come back to the same array over here. So by using ambient noise cross correlation, now not only we can extract surface wave, we can also see robust body wave signal, particularly some of the core phases show up very clearly. And also, beside those two phases I mentioned, you can also see this other phases like PS and PCP, SCP, PCS. All those show up kind of nicely in this plot over here. And besides seismic wave, actually, one thing we kind of surprised us a little bit is that we can actually also see the air wave. So it's propagated around 300 meters per second. After we stack all the cross correlation, you can actually see there's a fake line over here, which is the air wave propagating with sound speed, basically. So one of the questions we try to answer for this is whether we need to stack a whole US array to get a result. And the answer is not. Actually, even for a small array, such as all the stations within this yellow circle here, if you do cross correlation and stack the cross correlation, you can clearly identify the body wave phases, SCS and PKIKP2. And in fact, we can measure travel time for these two phases, so SCS and PKIKP2. And this here shows the preliminary result if we basically use different subarray and try to study this travel time of SCS and PKIKP2. And you can see that in general, SCS on the western side, the travel time is a bit larger. That means the velocity structure in the western side is slower, which is probably likely affected by the upper mantle structure in the western US. And the same is similar for the PKIKP2 phases. So in general, on the western side, the wave takes longer to travel down and back up. And this likely affected by the upper mantle structure as well. But again, PKIKP2 is actually goes through the inner core as well as the other side of the Earth. So it's a little bit more complicated to explain this. And one of the things we are kind of interested to do is right now we are asking the question whether this new technique can be used to study inner core anisotropy. In particular, because we have some seismic station in Antarctica region, traditionally it's very hard to get an earthquake in Antarctica. And so we don't really have a lot of ray path going through the inner core near the pole axis. So, but if we can use this method to extract wave based on seismic interferometry, we can actually create a virtual source in the Antarctica region, potential which will allow us to study the inner core a little bit better. So here I'm going to show some preliminary results for these 5 different arrays, and we do cross-gradient on them and stack them. And look, the PK-IKP2 phase, we can actually see a clear signal in all of these 5 arrays. And in general, the high latitude, like Alaska array and Antarctica array, the signal tends to arrive a little bit earlier compared to low latitude, like Peru is near equator. And so usually the signal arrives later for equator station arrays. And you can actually, if we make a travel time measurement, you can see that actually you can see this type of latitude dependent of travel time. And we can fit a kind of a best fitting curve on it. And right now we are trying to investigate whether this variation is due to just the simple difference between radius in equatorial direction compared to pole direction, or is there any anisotropy signal we can see from this type of signal? So this is the deeper part, mostly I'm going to cover, and I'm going to go back to the surface wave tomography part, which will, oops, so actually there's one more slide. So here is the slide that if you do cross-correlation between long distance station to the US array, actually not only you can see the surface wave over here, you can actually also see a lot of direct, this is direct P, and this is probably direct S, and there's a lot of other body wave phase that can be extracted. And we are trying to identify what those phases are at this point. So let me go back to the surface wave tomography and try to show off some of the results of us to study shallow structures. So I'm going to mostly focus on Rayleigh wave. So for wave propagate through array, the first thing we can measure is how fast this wave move across this array. So basically what we're going to do is try to track one of the phase and see how fast it moves across the array. And here I'm going to show an example based on one earthquake coming from Curio Island. So here's the earthquake, here's the waveform go across the US array. And if we bend past the signal to 60-second Rayleigh wave, then we can measure both travel time as well as the amplitude of the Rayleigh wave. So on the left-hand side is the travel time, where the red represents the wave arrival earlier, so travel time is small, and the blue represents travel time is larger, means the wave arrived later. So you can actually see how the wave move across the US array from northwest to southeast. And we can also make amplitude measurement shown here, where blue represent high amplitude and red represent low amplitude. And you can see this kind of striping pattern, which suggests there's some sort of multipassing effect in the observation. So there's some wave interference when they go across this region. So the way we can use that travel time map and amplitude map to resolve phase velocity is based on what we call this a kernel tomography method and Helmholtz tomography method. So if we look for high frequency approximation, which is ray theory approach, then the gradient of the travel time will tell us the slowness, which is the inverse of phase velocity. Also, the gradient of this travel time will also tell us the direction of wave propagation, shown here. However, this is just a high frequency approximation. If we want to consider the finite frequency effect, the full expression needs to include amplitude terms. So it's not only the gradient of travel time now, you need to actually add another correction term, which is the Laplacian of amplitude shown here, which should give us better estimation of the phase velocity shown here. So let's see, go back to the example I shown. So based on that Curio Island event for 60-second Rayleigh wave, here's the travel time map, here's the amplitude map. And the first thing we can do is take the gradient of this travel time map, and then this is what we derive. So basically, we can relate this as a parallel phase velocity. So you can see that if you estimate the phase velocity based on the gradient of travel time, you can actually see a slow anomaly shown here, which is like kind of weird. It's striking, and it does not relate to any surface geologic feature. However, if you compute the Laplacian correction term shown here, you can also see a striping pattern, and it's kind of anti-correlated with what we see in the gradient of travel time. And if you add these two terms together, the striping pattern kind of cancel out each other, and now you can start to see some of the very clear slow anomaly related to geologic feature. For example, here the slow anomaly is related to the Snake River Plain Yellowstone hotspot track, and here the slow anomaly is related to the Southern Rocky. So by using this method, for each earthquake, we can produce a phase velocity map. And although the single earthquake, the result doesn't look that great, but we do have earthquake coming from different direction. And similar for ambient noise application, we have staging coming at different directions. So we can measure this type of map repeatedly, phase velocity map repeatedly, and try to determine phase velocity structure at each location. So here shows the example of two locations at 3 different periods. So here's 12 seconds, 26, and 38 seconds. For this location, we have a source coming from all different directions for both ambient noise and earthquake. And if we measure the phase velocity for wave coming from different directions at that location, you can actually determine what we call directional dependent phase velocity measurement. So you can see for different azimuth, from 0 to 360, you can see there's some sort of variation in terms of phase velocity. And actually, you can see that in all these cases as shown here. And so by look at this type of measurement, we can determine both isotropic structure, which is the mean of this sine function. We can also determine the azimuthal and isotropy parameter, which is the amplitude of this sine function gives us the strength of anisotropy. Also, the peak of this sine function tells us the direction of fast direction. So we can do this for different period and at different location. And here shows the isotropic result in the Western US at 3 different periods, 10 seconds, 30 seconds, 80 seconds. And now you can start to see a lot of features that corresponding to known geologic features. So for example, for the 10-second map, the phase velocity is particularly sensitive to structure in the upper crust to middle crust range. And you can see the slow anomaly in the Central Valley, and also the Green River Basin over here. And some of the others basins also show up very nicely. And the high velocity is mostly related to mountain ranges such as the Sierra Nevada, as well as Colorado Plateau. And if you go to 30 seconds, then you start to sensitive to deeper structure. It's mostly lower crust, upper mantle. And now the most striking pattern is the slow anomaly, for example, in the Snake River Plain here. And also in the Southern Rocky, it shows up very clearly. Actually, in general, the edge of Colorado Plateau show up very nicely with slow anomaly. And here is the high lava plain. And if you go to 80 seconds, it starts to sensitive even deeper. It's mostly upper mantle structure. Again, Snake River Plain, Yellowstone show up very nicely over here. And the edge of Colorado Plateau show up. And now we can also start to see the subduction of the Juan-de-Fuca plate over here, as well as this delimitation feature or remnant slab feature, Isabella anomaly over here. And also in general, on the western side of US, we have more slow anomaly, suggest the mantle is likely hotter. And that's probably why on the topography I showed in the very beginning, we have this rough topography on the western side, and it's also higher in elevation. On the eastern side, its fast anomaly is mostly likely corresponding to colder mantle structure, and that's probably why it's tectonic more stable. And here I just want to make a quick comparison to the study like done before we have US array and this new tomography method. So this is Vanderly at in 1997, and you can see that without US array, it's very hard to separate some of the small scale feature we can see right now in our tomography. So hopefully this will convince you that US array is very valuable, and the new methodologies really help to improve our image of the Earth. So besides isotropic structure, we can also map out the azimuthal anisotropy. So at 3 different periods, 12, 26, and 38 seconds, for each location, we can determine the azimuthal anisotropy of Rayleigh wave. So each red bar here represents the anisotropy, where the length of the red bar represents the strength of the anisotropy. Here is the 2% reference. And also the fast direction is pointed by the direction of the red bar as well. So I will discuss more about anisotropy later when I talk about 3D model. But here, I just want to kind of see that at short period and long period, we do have very different anisotropy pattern. For example, in the basin and range, the anisotropy kind of turn from west to the eastern side. On the other hand, at 12 seconds, it's mostly in the same direction. So which suggests the crust and upper mantle have different anisotropy, which will show up in our 3D result I'll show later. And beside the phase velocity we measure, there's actually 2 other parameters we can also determine, we can also measure. So first one is actually the elasticity of the particle motion of Rayleigh wave. So here you can see that not only the wave propagating show up in vertical component, it's also show up in radial component. And in fact, the ratio between vertical and radial component is also affected by the structure right beneath that station. So by measuring the vertical and radial ratio, we can measure this what we call HV ratio, which is horizontal to vertical ratio. And besides elasticity, another thing we can measure is called amplification. So basically what amplification tells us is that if the wave coming through here, for example, if you have a slow anomaly right beneath here, usually the amplitude will go up. So in other way, if another side to say this is that if you can measure how the wave amplitude change from location to location, you can infer for a structure down in here as well. So use the same example from the Curie Island event coming from northwest direction. For 2 stations here and here, again, if we bandpass the signal to 60 seconds and measure the Rayleigh wave, we can see that the particle motion for these 2 stations are very different. For example, for the station in the north, this one is in Green River Basin, and you can see that they have stronger amplitude in the horizontal component, has higher HV ratio, so it's fatter in a way. And for this one in the kind of located on top of Southern Rocky, you can see that the particle motion is kind of elongated, and so it's higher in the vertical component compared to the radial component. And that's why we can say this is a low HV ratio. And we can do this type of measurement for all station, all earthquake coming from different direction for all different stations, and determine the HV ratio maps. So, and we can do this for ambient noise as well, although I haven't discussed how we can do that, but actually we already done it. And here's the result at 8 seconds. And this is 30 seconds based on earthquake. Here's the result based on earthquake as well at 60 seconds. And again, you can see that they actually corresponding to a lot of known geologic features. For example, a lot of high HV ratio observed in these maps are corresponding to some of the large sedimentary basins. So this is Williston Basin. Here's the Denver Basin. So they all show up very clearly. And in this measurement, HV ratio is actually particularly sensitive to very shallow structures. And one of the nice things is that it now allows us to push the inversion to up 3 kilometers. Actually, we can push up to 1 kilometer if we can include ambient noise results shown here. For example, if you look this area in Columbia River Basalt area, here you can actually see at 30 seconds, it suggests the HV ratio is high, suggests there's slow anomaly near the shallow part of this region. But if you go to 8 seconds, you can actually start to see low HV ratio suggests actually near the top you have very high velocity anomaly. So what this means is probably represent the shallow basalt at the top 1 kilometer, but then beneath the shallow basalt you actually have some sort of slow sedimentary basin, which you will only see it when you go to longer period. So by including all these measurements will allow us to study shallow structure a little bit better. And I'm not going to describe how we can get to the amplification map, but it's described in one of our paper. And you can see that at 30 seconds, we can, for blue region, represent that the wave always get amplified in that region. And for red region, it's always, the wave always kind of have smaller amplitude. So you can see that this is clearly correlated with the Southern Rocky area. And also longer period, it starts sensitive to deeper structure. Now you can start to see the Snake River Plain. And basically by using these information, we can infer for structure in the cross and upper mantle as well. And of course, the future goal is to try to include not only the phase velocity, but also amplification and HV ratio. So you have these 3 types of measurement, and they have different sensitivity. So this is depth, and this is phase velocity, this is amplification, this is HV ratio. They have different sensitivity to VS, VP, and density. So VS is red, VP is green, and density is blue. And you can see that they have all very different sensitivity kernels. And the future goal is trying to combine all these 3 types of measurement and do a joint inversion to infer all 3 parameters. But right now, what we have already done is try to joint invert for phase velocity as well as HV ratio. So here shows the phase velocity measurement at that particular location. So we take the phase velocity from our phase velocity maps for different periods. So from 8 seconds all the way to 100 seconds. So different phase velocity show up here, and you can see this is nice dispersion at this location. And also we can take HV ratio for different periods from our HV ratio maps. And here shows the result from 24 to 100 seconds. So here in this inversion, I haven't included the ambient noise result, which will, in principle, allow us to extend from 8 to 24 seconds. And so the idea is right now with this type of measurement, what we want to do is try to find a 1D structure right beneath that location so that we can explain both these measurements. So the first thing we try to do is try to find a VS model that can explain this observation of phase velocity. So in the first inversion, we didn't involve the HV ratio at all. So we only try to feed the phase velocity by invert a VS model. And density and VPVS, we use a reference model in the area, and we do not perturb them. So in this case, now we can find a 1D model that explains the phase velocity very well. But the predict HV ratio of that 1D model does not explain our HV ratio measurement at all, which suggests that if we include the HV ratio, we can actually provide additional constraint. So the second inversion, we are going to use this HV ratio as an additional constraint. And again, I'm only perturbing VS structure over here. And you can see that now the joint inversion actually prefer a much slower anomaly near this area. So this top 3 kilometer actually prefer to have velocity VS structure a little bit beneath 2 kilometers per second. And now we can still expand the VS structure, the phase velocity structure fairly well. And at the same time, can fit the HV ratio much better. And actually, we know the structure here pretty well, and because here there's a lot of oil and gas exploration here, and we know that there's around 3 kilometer thick sediments over here, which is consistent with what our new inversion suggests. However, if you look the HV ratio prediction, it still not fit the observation very well, which suggests that by just perturb VS model is not enough to explain our observation. So the next step, we are going to allow both density and VPVS ratio to change. In this, the third inversion now, not only VS is allowed to perturb, we allow density and VPVS ratio to perturb as well. And you can see that in our model, it actually prefer a lighter material, a smaller density at the very shallow part, as well as high VPVS ratio in the very shallow part, which is consistent with the knowledge that there's a 3-kilometer sediment over here. And also, if you look at the prediction, now it can explain the phase velocity as well as HV ratio pretty well. So by include this new information of HV ratio, it allows to resolve the shallow structure of the top 3 kilometers, not only VS structure, but also density as well as VPVS ratio. And actually here shows the result of the inversion for the top 3 kilometers at all different locations. And you can see that we now see all the slow anomalies are mostly related to major sedimentary basin. So for example, here is the Central Valley and Green River Basin, Denver Basin, Powell Basin, Williston Basin all show up very clearly. Actually, you can see that in this area, this is the Black Hill, which is show up as high velocity because there's no sediment there. And besides slow anomaly in those sedimentary basins, we also see small density, such as here. This is a Green River Basin. And then all other major basins show up as you need to have light material in the top 3 kilometers, and also high VPVS ratio as well, shown here. So in a way, this shows that potentially using this joint inversion method, we can resolve top 3 kilometers, but not only VS, but also density and VPVS. And if we plot the deeper structure at 80 seconds, we can now start to see metal structure. For example, we can start to see the subduction of Hondifuka plate. And if we cut 2 cross-section, AA plane, BB plane, then we can see the clear signal of the subduction of Hondifuka plate. And this can be compared with the kind of dynamic model in the area. And if we look at the BB plane, then this cuts through the Snake River Plain, Yellowstone. And you can see that the slow anomaly in the mantle show up here and connect all the way to the Yellowstone hotspot. And this can be compared with the Prue model proposed in this area. And also here is still the subduction of the Hondifuka plate show up here. And besides isotropic structure, we can also see the anisotropy structure very well. And on the left side is the anisotropy at 15-kilometer depth. And on the right-hand side is the anisotropy at 50-kilometer depth. And you can see that in the background, I plot the isotropic structure. Here you can see that in the basin and range, the anisotropy mostly point in the same direction. On the other hand, the anisotropy in the upper mantle, it has a big turn over here. So in a way, it suggests that the deformation in the crust in the upper mantle is probably different in a way. And also, if you look the upper mantle near the San Andreas fault, we can start to see this fault parallel anisotropy signal very clearly. And where we have this change direction of fault, we also have this change direction of the anisotropy pattern. And the north of the triple junction, actually, we also see a abrupt change of the anisotropy pattern. So right now, if you go to the north part, this is in the subduction regime, and the anisotropy is mostly point toward the direction of subduction. So in a way, by having this anisotropy will allow us to potentially constrain the deformation process a little bit better. And just before I end my talk, I just want to point out that not only the method I described can work on like US array, it can also work on some of the regional array. For example, here we have a seismic array in Long Beach, California. So this is a very dense array. The dimension is 7 kilometers times 5 kilometers, and we have more than 5,000 stations in this area. And the reason why we have this nice array is because there's oil field here, and the oil industry would like to explore the structure here a little bit better. So here's the overall Southern California area, Los Angeles Basin, and Long Beach oil field is this one shown here. And you can see there's like maybe 100 years ago, there's a lot of oil field in this area. And so the company is interested in looking at the reflection signal. So they have this vibrator drive. They drive around the city and try to create an active source. And let me just show one of the example. So they put a vibrator here, and after the signal start, you can see the P wave move out. And also you can see there's a lot of. So let me play this one more time. So you can see the P wave move out, and also you see a lot of linear feature. Actually, those are the busy roads, busy highways in Southern California. So there's a lot of traffic noise. On the right-hand side, I'm going to show the result after we do this ambient noise cross-correlation, and basically do the cross-correlation between this point to all other locations and create a virtual source. So in a way, it's due to passive signal, and you can see there's a lot of basically all the surface wave propagate outward very nicely, and we can use this signal to study very shallow structures. And the best part is that the noise is free, and it's very expensive to do this vibrator source. And so again, we apply the same tomography method. So, and we can measure for different location A, B, C, for example, for wave propagating in different direction, different phase velocity. So you can again see very clear and azimuthal and anisotropy signal at all these three different locations. And again, the red bar here represents the anisotropy. And notice that here the anisotropy is much stronger. Here in this small red bar is 10%. So a lot of this is around 10% anisotropy. And also notice that the period range we are interested in right now is much higher. So here's 1.25 hertz. And it's mostly sensitive to top 200 meters. And for 1 hertz, it's go a little bit deeper, but it's still mostly top 300 meters. And you can see that an anisotropy pattern here actually turn a little bit more related to the fold direction. So at this point, we are still trying to figure out where this anisotropy come from. But one of the most likely case is that in this area, we have a maximum component compressible stress in the north-south direction, which will close the microcrack orientated in north-south direction. And because of that, that will make the anisotropy basically faster for wave propagating north-south. So in a way, by studying this anisotropy, potentially will allow us to study regional stress field. And of course, we can study the 3D structure, which is shown here in the top 1 kilometer in this area. So here's top at 100 meter is the slice at 100 meter, 300 meter, and 650 meter. And you can start to see some very shallow structure. At the top 100 meter, mostly we see the slow anomaly south of the Newport Inglewood fault in this area. So this is a very active faulting. It's part of the San Andreas fault deformation. And well, it's not the San Andreas fault, but it's the same deformation zone area in the Southern California area. And in the deeper part, you start to see this fast anomaly kind of associated with this Newport Inglewood fault. So if we cut 3 cross section, A plane, B plane, and CC plane, and again, what you see is that in the south of the fault, we actually see a lot of slow anomaly, but in the north part of the fault, we see a lot of fast anomaly, suggests that there's very different, very distinct geologic feature in the south and the north. And actually, we know the aquifer system in the south is different from the north. In the south, it's mostly seawater. In the north part, it's mostly fresh water. And if we go to deeper structure, now we can start to see this fast anomaly kind of relate to this fault zone. And actually, if we plot the topography on top of our tomography, you can see that the high velocity structure at 60, 50 meters is mostly related to this signal hill feature shown here. So the likely scenario of why this happened is that during the deformation, there's kind of deformation pushed the deeper material up to near surface. And because the deeper material usually is faster, and that's why we see this fast anomaly. And actually, it's mostly likely because this kind of deformation, it creates a reservoir for oil. So there's a lot of oil production in just right on top of this signal hill area. And here just show that beside the surface wave, if we stack the signal, we can also start to see body waves such as P wave and S wave shown here. So potentially, there's a lot of potential to use this type of method to not only study surface wave structure, but also study structure based on P and S wave. So here I just do a quick conclusion. Seismic interferometry allows both surface wave and body waves propagating between station pairs to be extracted using noise signals. High-resolution surface wave tomography is now allow detailed crust and upper mantle structure to be studied. And by combining different surface wave measurements, such as HV ratio and phase velocity, it provides additional constraint on not only velocity, but also density structures. And finally, there's ongoing study trying to extract body wave by seismic interferometry, and it's likely going to become a new important tool for Earth imaging. So thank you for your attention, and I'd like to take some questions.
Great. Well, thank you very much, Fanchi. That was absolutely fascinating. I was familiar with that survey in Long Beach, but I hadn't seen any of the results from it yet. It's just pretty powerful work. So yeah, very cool. Thank you very much.
Thank you.
And so I have one question so far in the window. I would encourage everybody else, while I go through that first one, if you have any questions for Fanchi, please ask away. We have plenty of time. It's not like we have to leave the room because a class is coming in. So I'll start with the question. First question is from Rob Porritt. And Rob was curious about what do you think some of the possible physical sources are that are generating the noise signal for the body waves?
Okay, so I guess the question is mostly for the result that I show for the core phases observed using US array.
I think so, yeah.
So actually I have some few additional slides. So what we think is actually those signals are coming from earthquake coda. So although we try to remove earthquake, if right after a big earthquake usually have a long coda, and those coda actually have very small amplitude, sometimes smaller than even the background noise. And in that case, we do not remove them from our signal. So in principle, when we cross-correlate our ambient noise, we include some of the earthquake coda as well. And here shows some of the monthly stack from the cross-correlation we done in the US array. And so here is from each month is from 2007 all the way to 2011. And you can see that the radio wave basically is strong at all the months. But you do see some sort of variation, temporal variation for the SCS signal shown here. So some months is very weak, some months is stronger. And also it's the same pattern for the PKI-KP too. Some months is stronger, some months is weaker. And the first thing we thought is that try to check whether there's any seasonal variation, but apparently it's not really depend on seasonal. And the second thing we try to check is whether it's related to earthquakes. And the result is shown here, like for each monthly stack, if we plot the amplitude of SCS and PKI-KP2 phases, and you can see that the variation is somehow correlated with the global seismicity, which is shown in blue. So we calculate this seismicity, global seismicity, based on the number of earthquakes larger than 6.3. And then you can actually see that wherever we have large amplitude of SCS and PKI-KP2 phase, we actually also see strong, like more seismicity in that month. So you can see that mostly they correlate very well, and which give us confidence that, well, basically we're suggesting that a lot of the body wave phases we see in the cross correlation is coming from earthquakes.
Okay, great. Next question is from Lena Constanza Garcia Cano. And Lena's question is, do you think that this sort of tool would be useful for imaging volcanic areas?
Yeah, I think the answer is for sure. So there's several techniques I think can potentially work very well for volcanic area. Particularly the HV ratio is probably very interesting because it potentially will allow you to study very shallow structure, and not only the VS structure but also VPVS ratio, as well as density. So I think, well, I think the answer is for sure. And the body wave part, I think there's also possibility you can extract body wave based on cross correlation and use it for volcanic study. Yeah, I mean, I actually am looking forward to apply some of this method for that application.
Cool. Next question is from Lanbo Liu. And Lambo is curious, what is the length of the record for the ambient noise data set that was collected at Long Beach?
I think we have 3 months of data. So we done 3 months data cross correlation. Actually, the data is huge because original when we got the data is 250 sample per second. So actually the whole Long Beach array, the data we got is larger than the whole IRIS data set. And we actually need to decimate it by quite a bit in able for us to process it. Otherwise, it just will take forever. And in fact, Dongzhu Li, who is a student at Caltech, who helped me to calculate all this cross correlation, is using GPUs at supercomputers in Caltech to do the computation. Originally, I'm using like 12 CPUs, and it takes me like a couple of days to even just finish a day of cross correlation. But now he can do like 3 weeks of cross correlation just using all the GPUs in 1 day. Basically, right now, with a lot of new computational resource, now we can perform this cross correlation in this kind of large data set.
Awesome. That's just incredible that it was larger than the IRIS data set as its sampling rate and station count. It's incredible. I had a question related to this experiment as well. The sensors that are out, are those just basically high frequency geophones, or is there a specific sensor type that they used?
Yeah, it's basically high frequency geophones. They have some particular device, so they can kind of keep rotating them. But basically, it's a vertical component geophone. And actually, we are not supposed to see signal. Actually, the corner frequency is 10 hertz. So it's kind of surprise to them that we can actually see surface wave down all the way to like a couple seconds period.
Yeah, that's impressive. Okay, well, the next question's from Yang Shen, and Yang's question is, how do you deal with the trade-off between VP and density at shallow depth?
Right. So I guess the quick answer is that there's definitely trade-off between density and VPVS ratio that cannot be completely resolved by our data set. So we do introduce some sort of empirical relationship between different parameters such that we can avoid the trade-off. But for this sedimentary basin particularly, both the density, you can see that it's require very light material, it's very high VPVS ratio already. So in a way, for this region, it kind of push to all the range we allowed the model to perturb already. So in this region, we actually do not require any empirical relationship between them because they just Otherwise, they won't fit the data. So they both need not only extreme density, but also extreme VPVS ratio. But it is true that for other regions that we have trade-off between density and VPVS ratio. And that's why in the future, we'll definitely try to look into use amplification as an additional constraint, which potentially will help us to avoid the trade-off. And we also look into trying to involve receiver function, and hopefully we can resolve VPVS ratio that way, and potentially that will also give us some way to avoid the trade-off.
Okay, great. The next question is from Jim Nee, and Jim's question is seismic anisotropy generally much larger in the uppermost mantle or in the crust?
I think in general it's larger in the uppermost mantle, and the anisotropy we can get from ambient noise is mostly middle crust, lower crust anisotropy. So they are usually around 1%, and anisotropy in the upper mantle, particularly in region with slow anomaly or near plate boundary, they can often larger than 2%. So I think on average it's larger in the uppermost mantle.
Okay. Next question is from Paul Bremer, and Paul's question is, are more signal stacks needed for the long distance ambient noise cross correlations compared to the short distance?
So I guess the question is the duration of the noise, how long you need to do the cross correlation. So it is true that for longer distance, you do need to use longer noise signal. For example, for US array, usually for a 500-kilometer distance, you probably need like a month of data, so you can start to see nice surface wave. But for Long Beach array, each station is just like 100 meters apart. In that case, you probably just need a day of noise and you can see robust surface wave. But if you are talking about the earthquake, the body wave, then that really depends on the seismicity. And sometimes you have a lot of seismicity and you can just do some cross correlation during that period of time, and you can start to see strong body wave signals.
And there was a follow-up question from Paul, just related to the noise sources. In that case, are the noise sources generally the same?
No, the noise source is very different from period to period. So for long period, or like for microseismic and band, basically it's mostly from oceanic direction. But if you go to higher frequency, like the one we show in Long Beach, when you go to 1 hertz, and the signal seems to be more localized. So a lot of them still coming from the ocean, but it's probably from very near shore, like maybe the water break on the coast, which create some sort of noise. We can also see some like traffic signal and also airport air flight landing in that. There's an airport in the Long Beach array. And so there's definitely more civil activity when you look at a much higher frequency signal. So it's really period dependent and sometimes location dependent as well.
Okay, great. Well, if there aren't any other questions from anybody, I'll just give you anybody one moment if they have one last question they'd like to sneak in. But I just wanted to say thanks again, Fan-Chi. We got a lot of nice comments in the window from people who enjoyed the talk, and I thought it was some pretty impressive work. So I just wanted to say thanks again, and
well, thanks for inviting me. It's my pleasure.
Yeah, no, it's our pleasure. It's great to see, in particular with this webinar, it's great to see such amazing research come out of the US Array. I mean, this is exactly what it was designed for, so it's great to see it happening.
Sure, sure.
Yeah, so, okay, well, I don't see any more questions, so Fan-Chi, I'll let you go. Thanks again.
Thank you.
And everyone out there, this has been recorded, and I'll be posting it in the next day or two, so if you want to check it out again, or you have somebody else that you know would like watching it, it'll be available on our webinar page. So thank you, Fan-Chi. Thank you, everybody. And we'll see you here next time.
Thanks. Bye.
Bye.